Every year, more than 1 trillion microchips are produced worldwide. In technology hubs like Taiwan alone, thousands of units are completed every second. With a global market valued at over $600 billion, these tiny electronic brains are the real driving force of the modern economy. But do you know how they are made? Discover the astonishing process of producing millions of microchips in a semiconductor factory. Today's microprocessors contain billions of transistors on a single chip. Most of today's electronic devices use one. In 1958, the inventor of the integrated circuit, Jack Kilby, managed to place a single transistor in his design. The latest generation uses almost 1 billion transistors, and according to Moore's law, that number doubles every 2 years. This company produces 70 billion microchips per year for devices ranging from washing machines to smart cars. And each one of them is a miracle of miniature manufacturing. A processor works thanks to circuitry made up of millions of individual components called transistors. The more transistors we put on a chip, the faster and more powerful it will be. In this strange and futuristic-looking factory, silicon wafers are produced, which are the basis of all microchips. The substrates for microchips are made from sand, quartz sand, and are called silicon wafers. Silicon has special properties because it is what we call a semiconductor. This means that, depending on how it is treated, silicon can conduct or block electric current. It is this property that makes it perfect as a base for the millions of tiny transistors needed to make a microprocessor. The problem is that, since these transistors are so small, the silicon base on which they rest needs to be absolutely perfect. It took decades to perfect the process of producing silicon with a perfect monocrystalline structure to manufacture these wafers. It starts with polycrystalline silicon, which is heated to about 1,420 degrees Celsius inside a special sealed furnace. This furnace was purged with argon gas to remove the air. The molten silicon we obtain is spun in a crucible, and from this purified molten mass, a huge monocrystal is extracted. The result is a silicon crystal that weighs about 200 kilograms and has a diameter of about 200 millimeters. However, impurities pose a threat to these flawless silicon crystals. The crystal is so strong that it supports its entire weight with a single wire 3 millimeters thick. Thus, after several tests with chemicals and X-rays, it is placed in a silicon wafer cutter. The result is a silicon crystal about 200 millimeters in diameter. The result is a silicon crystal that weighs about 200 kilograms and has a diameter of 200 millimeters.
Mas, uma vez cortado,
Millimeters. The result is a silicon crystal that weighs about 200 kilograms and has a diameter of 200 millimeters. With this modern polisher, the wafers are not smooth enough, so further polishing is necessary. The result is silicon wafers with a surface roughness of less than 0.1 nanometers, already completely polished. Now, finally, they are ready to start with the circuit design. Using computer-aided design software, the engineers create the detailed design. Once completed, a thorough check is carried out to ensure that it meets the required specifications. Next, 25 wafers are packed in each hermetically sealed container and sent on a journey that will take them through hundreds of manufacturing steps. Placing millions of transistors on the small wafers is the job that chip manufacturers do. The problem for this factory is that these transistors are about 200 times smaller than a red blood cell, and making something that small is a huge manufacturing challenge. Fortunately, there is a machine that does this. It's a photolithography machine, and it can print trillions of transistors on silicon wafers every hour. Before entering the machine, each wafer is coated with a light-sensitive liquid called photoresist. It reacts to light like camera film in a darkroom. Photoresist is a very sensitive chemical agent. That's why yellow light is used in this room. Otherwise, normal daylight would ruin the wafer. Photolithographic techniques transfer the circuit structures onto the wafers in a way similar to slide projection. The machine emits a laser that passes through the design blueprint of a transistor and engraves it onto the silicon wafer. just like in a photograph. This leaves an image of the transistor on the wafer. When the chemical is removed, the design remains. To place all the components on the wafer, this has to be done layer by layer. They make the wafers go through the same cycle up to 40 times, repeating the process and leaving unexposed areas unetched. The transistors are built level by level, like miniature skyscrapers. The result is hundreds of microchips, each containing more than 1 billion transistors. The downside is that, to meet the demand for increasingly powerful devices and computers, the number of transistors on a chip needs to double every 2 years. The biggest challenge for engineers is to find new ways to improve the laser beam that etches the shape of each transistor. They discovered that by passing the beam through a layer of water, it behaves like sunlight passing through a magnifying glass. It increases the intensity of the beam and reduces the size of each transistor, making it about 5 times smaller than the smallest existing bacterium. But building machines that depend on this kind of precision is a real nightmare. It takes 3 months to assemble and test the 800 circuits, 1,300 cables, and 400 boards that make up these water-enhanced machines. Working on this microscopic scale is a big problem. When a transistor is only 1/10 of a thousandth of a millimeter wide, the smallest speck of dust can cause the electronic equivalent of a short circuit. A single particle can destroy a chip. So before they start working, the employees must put on protective suits. The manufacturing process takes place in a clean room covering almost 18,000 square meters. Thanks to 12,000 tons of air conditioning equipment, the air in this room is 1,000 times cleaner than that of an operating room. Each employee must take an air shower every time they enter to eliminate invisible particles. And all the air inside the factory is renewed, every 2 minutes, making it 10,000 times cleaner than the outside air. Copper dominates the next stage of the process. The thinnest interconnection wires connect billions of separate transistors to form the integrated circuits. Before pouring copper into the grooves for the interconnections, a barrier layer is applied to prevent short circuits and ensure reliability. Next, the grooves are filled with copper, and the excess is polished down to the edges, thus isolating each interconnection from the others. In 2 months, the wafer is ready. The finished silicon wafers carry up to 1,000 different microchips and more than 4 trillion circuit components. Now all that's left is to cut and trim, and the long journey from being sand to a circuit board will be complete. The final stage of microprocessor production is encapsulation. To prepare for this step, tin and silver granules are applied to the wafer. They will connect the chip to its base structure. What was once just a pile of sand with no value can now be sold for hundreds of dollars per gram. And that was today's video. Don't forget to leave a like and subscribe to the channel.